Just a little. Put a little more on the screen. How are we feeling about the integration? I know the numbers are messy, but that's okay. We're just going to leave them messy. Pretty sure that's why he didn't ask you to do the expected value. He didn't really want you to have to take the square root of 2 and cube it, but we can just do it with messy numbers. I'm going to go ahead and pull that 2 out in front so that this looks like x squared. And I can go ahead and integrate that. So I would have x cubed over 3. But since I had that 2 out in front, that would be 2x cubed over 3. We're going from -1 to the square root of 2. And we're just going to leave it. We're not going to bother trying to simplify it. Just going to call that 2/3 of 2 to the 3/2 minus -1 cubed. Sure. We'll just go with that. Now, I said that we should get a number between -1 and the square root of 2. I would probably have to put that into a calculator to figure out if it's between -1 and the square root of 2. That is not worth our time. We're just going to call it good and say, yeah, we probably got the right answer. Should we take a look at the next one? And I'll make up some bonus problems for the next one too. So the next potential distribution we've been given is f of x equal to 1/3 on 1 to 4. And I'm going to go with we've got options for how to deal with this. But if we stick with this same idea, if I'm going to show that it's a PDF, we're really being asked if we integrate this function from 1 to 4, is it equal to 1? I think it should be. If I integrate 1/3 dx, I'm going to get 1/3 of x from 1 to 4. So I'd have 4/3 minus 1/3, and that is 3/3 or 1. But I'm going to pause for a second and say, name that distribution. This is actually called the uniform distribution. He didn't tell us that at the time, right? But in the end of chapter or section 9.3, this is a uniform distribution. A uniform distribution is like the most boring distribution.
Is this the one that's just like a horizontal?
Totally. It's just a horizontal line. And generally speaking, for our uniform distribution, our like PDF equation is just that f of x is equal to 1 divided by b minus a. So in this case, that would be like 1 over 4 minus 1, because that was our b to a. By the way, for the uniform distribution, does anyone remember the formula to get the expected value? Sorry? Yes, expected value is the same as the mean.
Doesn't it just equal whatever?
Well, if you're not sure, guess what? We can integrate it to figure it out. So in terms of those special continuous distributions, only the normal distribution can we not integrate. For both the uniform distribution and the exponential, if you don't want to memorize more stuff, you don't have to. The integrals are pretty straightforward. This one especially. So if I integrate from 1 to 4, 1/3 x dx, I'm going to get 1/6 x squared from 1 to 4. So I would have 4 squared over 6 minus 1 squared over 6. 4 squared is 16. 16 minus 1. Mathing right? You all can stop me if I'm not mathing right. So I'd have, what was that, 15 over 6. Those are both divisible by 3. So that would be 5 over 2. And we can get that by taking b plus a divided by 2. Should we find the variance also? Just because we can?
Isn't it zero? Is that uniform?
It is a uniform distribution. So if you've got it memorized, you're good to go. But if you don't have it memorized, we can still do it with an integral. So there are 2 options for how we would integrate to get the variance, right? So option 1 is that we basically use the same equation that we had for our discrete distributions, where we take x minus our expected value, whole thing squared, times our probability density function, dx. But in this section, we have another form for the variance, which says it's generally easier to integrate x squared times the PDF dx, and then subtract off the expected value squared. So if you didn't have the formulas memorized, it's still not that bad to integrate. If I integrate x squared, I'm going to get x cubed over 3, but I've already got a 3 at the bottom. So I'm going to get x cubed over 9 from 1 to 4. And then I'm subtracting off 5/2 squared. So if I plug in the 4, 4 cubed is 64. So I'd have 64 over 9 minus 1 over 9 minus 5 squared, that's 25 over 4. This whole thing would be 63 divided by 9. But 63 divided by 9 is 7. So I'd have 7 minus 25 over 4. And if I got a common denominator on that, 7 times 4 is 28. Y'all can stop me if I make a math mistake. But this would be 28/4 minus 25/4. And I think I would get 3 over 4 for my variance. Dun, dun, dun.
How does it vary at all with this uniform?
So, now I'm like getting nervous because that was not the thing I was expecting to see. Getting nervous, so I'm going back to check the book. To make sure I didn't mess something up. But I am pretty sure that for our uniform distribution, it should work out to be 1/12 of b minus a squared, which I think that works out to be. Okay. So the issue about the variance is variance takes into account the spread of the numbers, right? So this is saying all of the probabilities are the same, but not all of the X values. So the way that we would have zero variance is if we like had a list where every single, like if we had a list where every single number in the list was 3, that would have a variance of 0. But here, our X values do vary because they vary between 1 and 4. It's just that they all have equal probabilities. So we do have a variance. Yeah. Good times. So for a uniform distribution, it's probably faster to have memorized the formulas, but it's never going to be crazy difficult to integrate. So if you forget the formulas, you can always go back. Question. Yeah, so my standard deviation would end up being the square root of 3/4 or the square root of 3 divided by 2. How are we doing? Should we move on to another problem? Dun, dun, dun. I was just going in order on this, but I am happy to skip around if there's anything in particular that someone wants to take a look at. So our next one here for part 3, f of x is 3x squared on 0 to 1. And we've been asked to find the probability that x is in the interval from 0 to 0.4. That got a little messy. When we're talking about a continuous distribution, probability is represented by the area under the curve. So this question is the same as asking us if we have this function 3 times x squared on 0 to 1, this probability is saying what's the area between 0 and 0.4. So we're going to integrate from 0 to 0.4 of 3x squared dx. Most of these continuous distributions, at least the things that he's given us, they're all kind of easy to integrate. So we might as well. If I integrate 3x squared, I get x cubed. And I'm evaluating that from 0 to 0.4. So I'd have 0.4 cubed minus 0 cubed. My brain doesn't work well in decimals, so I'm going to write that as 4/10. No, I'm not. I'm going to write that as 2/5. Because that, I think I can manage to cube. So I would get 8 over 125. That's a pretty low probability, by the way. But, this question didn't ask us for this, but let's make it a choose your own adventure and add in the question and pretend that we were asked to find the median value of X. So that word median means we're looking for the place where exactly half of the area is below it and half of the area is above it. Or you can think about it as the place where your probability finally reaches 50%. So as an integral, I would be looking to go from 0 to what I'm going to call m for the median for this function. And I need that to equal 0.5 or 1/2, depending on whether we like fractions or decimals. My integral is the same. I'm going to end up with x cubed, but I'm going from 0 to m, and I need that to equal 0.5. Evaluating the endpoints, I've got m cubed minus 0 cubed has to equal to 0.5, which means that my median would be the cube root of 0.5 or 1 over the cube root of 2. And they're trying to run away. We were asked to compute the mean and the variance, but not the median. So that was our bonus question. But part 4 is referring to that same function, the asking for the mean and the variance. Should we do them? Good times. So my mean, or the expected value, we're looking for the integral from 0 to 1 of x times our density function of 3x squared. Luckily, we're still in the realm of pretty straightforward to integrate. I'm going to go ahead and pop that 3 out in front so that I've got 3 times the integral from 0 to 1 of x cubed dx. And when I integrate, I'm going to end up with x to the 4th over 4, or 3x to the 4th over 4 from 0 to 1. When I plug in 1, I get 3/4, and when I plug in 0, I get 0. So my mean is 3/4, which makes sense given my picture. I'm looking for a number between 0 and 1. And since the probabilities are bigger towards 1, I would expect it to be like closer to 1 than to 0, but you don't need to worry about having that intuition. As long as you got a number within the domain, we're good. To find that variance, I'm going to choose what our book calls the alternate formula. And if you were in a stats class, I would just call, like, that's how you find the variance formula. We are going to be integrating from 0 to 1, x squared times our density function. And when we're done with the integral, we subtract off the mean that we just found squared. I like to give lots of separation to remind myself I'm not integrating this piece. Question.
For the mean, for expected value, where did that extra x come from?
This x,
Yeah.
that's part of our formula for how we find the expected value.
Oh, you know, it's like x1 times near x1.
Yep.
Okay.
Yeah. So like when we go from discrete to continuous, that x stays there. The only thing we change is instead of having a summation, we switch it to an integral.
Okay.
Yeah. This formula looks a little bit different than the variance formula that we had for a discrete distribution, though there is a way to make the discrete distribution one look like this. This is usually the one that's easier to integrate versus the one that looks like x minus the mean whole thing squared times p of x. So I'm going to pop that 3 out in front. Going from 0 to 1, x squared times x squared is going to give me x to the 4th. I'll leave this piece out here. If I integrate that, I'm going to end up with 3x to the 5th over 5 from 0 to 1. Minus, and I'll go ahead and square this now, that's 9 over 16. So when I plug in the 1, I'll have 3/5. When I plug in 0, I'll have 0. So I've got 3/5 minus 9/16. I'm probably going to leave it there. But 16 times 5 is 80. So you could get a common denominator, but I probably wouldn't worry about it. I would just leave it there. By the way, if we were asked for the standard deviation, I would just give it as the square root of ugly. And walk away. And even though that's the most recent stuff, obviously that is not the only thing that we can expect on the exam. So within this stuff, he could test you on some of the techniques of integration, right? By just giving you probability density functions that are a little bit messier. Based on the practice exam, it looks like he's sort of separating those two things. So it looks like he's giving you things that are easier to integrate on the continuous probability distribution stuff, and then just asking you separately to handle some integration. We've got 20 minutes left. Should we handle some integration or do more practice with the continuous probability stuff? I'm good either way. I can just keep running through this test. Should we just keep running through this test? I see some yeses. Let's do that. -2 to -1. It is. It is weird. And I was going to say, I know why it's weird. So we're going to do this problem, but what if this had said, take the integral from -2 to 1 of 1 over x dx. Why would this have been a much worse problem to do? Oh, well, we're going to run into that problem with the -2 already. There's a different problem for this.
Wouldn't it be worse because you have to do like don't you have to split it at 0 and then you have to evaluate two different ones?
Totally. Yes, we'd have to split it at 0. That's why it would be worse. So good news. We weren't given this one. This one has a domain issue at 0. That's why he was actually being nice by giving us -2 to 2 or -2 to -1. Yeah, but you're right. We're going to have to deal with the natural log thing. So when we integrate this, we technically get natural log of absolute value of x. And I know sometimes we get lazy about the absolute values. I try not to, but it's easy to kind of forget about the absolute values. But this is when we really need it. So when I plug in -1, and then we take the absolute value, that becomes natural log of 1 minus natural log of 2 because of those absolute values. And that's a 0 minus ln of 2 or negative ln of 2. By the way, if we just think about what the graph looks like for a second, it makes sense that our answer worked out to be negative because the graph of 1 over x looks like this. So if we're going from -2 to -1, all of that area is below the axis. So we would expect that we should get a negative value for that integration. Does anyone want to do this one? No.
Yes.
Okay, yeah, let's do it. Let's do it. I think it's worth it, you know. So if we had encountered -2 to 1 of 1 over x dx, we would have to break this up to go from -2 to 0 plus 0 to 1 of 1 over x dx. And both of those are improper integrals because their boundaries are asymptotes. So I would switch this one to look like the limit as b approaches 0, -2 to b of 1 over x dx, plus the limit as a approaches 0 of a to 1 over x dx. There's another little subtle thing here. And on both of these, we really should be careful about like which side we're approaching 0 from. So all of the numbers between -2 and 0 are on the left-hand side of 0. And all of the numbers between 0 and 1 are on the right-hand side of 0. Now we're ready to integrate. I'm still going to have that limit as b approaches 0 from the left, natural log, absolute value of x from -2 to b, plus a limit as a approaches 0 from the right, natural log, absolute value of x from a to 1. Up a bit. So I've got a limit as b approaches 0 from the left. We're going to have ln of b minus ln absolute value of -2. And over here, our other limit as a approaches 0 from the right, ln 1 minus ln a. As I approach 0 for natural log, ln of 0 heads to -infinity, and I'm actually done. This diverges. Cool. Yes, we could finish the other ones off, right? That's going to be minus natural log of 2, but that's just a constant. So -infinity minus a constant, we're not getting any better.
How can you go to negative or something zero to negative?
So this says that we're a little bit to the left of 0, but because we're taking the absolute value of it, it's really just headed to 0.
Okay.
Yeah. Yep. And then I choose to just think about what a graph of natural log looks like to know that as we approach 0, that y value is headed to -infinity. Yep. Cool. How are we doing for time? 15 minutes. More time for questions. Let's do that next one. Oh, the next one is actually one of my favorite integrals, because I just think we should all memorize the answer to it. I mean, obviously you have to show your work on the test, but you should just memorize the answer to this one. In order to integrate natural log of x, I'm going to walk up to this integral and I'm going to say, it sure would be cool if there was a u substitution, but there's not. Because the derivative of natural log of x is 1 over x, and I don't have a 1 over x in the problem. So our only choice is to do integration by parts. And I've got a mixture of logs and nothing. So the nothing is secretly a 1 dx, and that's my algebra. Since logs come first in the word late, I'm going to let u be equal to the natural log of x. That means all the rest of it had to be dv. So dv is the invisible 1 dx, which means our v is x and our du is 1 over x dx. And when we write out our ultraviolet voodoo, we end up with x times natural log of x minus the integral of x times 1 over x dx. But the cool thing on that second integral is those x's cancel out, which means I've got x natural log of x minus the integral of 1 dx. And I choose to memorize that the integral of natural log of x dx is x ln x minus x plus a constant. You definitely would need to show this work on the exam, but for anyone who's hanging out with me for 16C also, it is worth for 16C just memorizing that the integral of ln of x is x ln x minus x. E to the negative 2x, cool. Questions about this before we? So when we integrate 1, we get x. Or x plus a constant, but. Oh, good question. Yeah, I did not add a co-class for 16C for next quarter, but I will totally have office hours specifically for 16 students. If y'all just tell me what time you want them next quarter, I'm good. And if that ends up sort of turning into a co-class, that's okay too. But no, I didn't add it because most of you are not taking 16C. You all could just continue hanging out with me and doing more calculus, even if you're not taking the class. I got no takers. Yeah. Okay. But like I said, the real challenge for 16C is trying to schedule something with enough people that works for enough people scheduling wise. So I really mean it. If you all pick a time that you for sure can do a co-class with me, I'll find us a room and make it happen. Continuing on problem 2 here. I've got x e to the negative 2x dx. And if I take a look at that, I'm always hoping for a u substitution, but it's not going to be helpful here. Because if I made that negative 2x my u, the derivative would just be negative 2, and it wouldn't take care of my x out in front. And if I tried making my u e to the negative 2x, then I need a whole nother e to the x thing. So I don't have a u substitution. We are going to have to do integration by parts. I've got a mixture of algebra and exponentials. A comes first in the word late. My u would be equal to x, which makes dv everything else. E to the negative 2x dx. And when I take that derivative, I get dx. And when I take the antiderivative of e to the negative 2x, I'm going to end up with negative 1/2 e to the negative 2x. And if anyone would like that in slow motion, I'm happy to do that. This guy shows up a lot, so it's kind of like I'm doing a mini u substitution with u being the negative 2x. So I end up with a negative 1/2 when we solve for du. Okay, got a request to show that. So if I integrate e to the negative 2x dx, I'm going to let u be equal to negative 2x, which makes du negative 2 dx, or negative 1/2 du is dx. And when we sub that in, we end up with negative 1/2 the integral of e to the u du, or negative 1/2. Integrate e to the u, we get e to the u back. So negative 1/2 e to the negative 2x. I don't know necessarily that you need to show this unless you personally need to show it in order to do it. Our book does give us a general formula for the integral of e to the ax being 1 over a e to the ax. You got points for not doing this? Oh, yeah, right. So for sure, like, this is worth partial credit. Might as well do it, right? So if we move on here to have u times v, we'll end up with negative 1/2 x e to the negative 2x minus the integral of v du, negative 1/2 e to the negative 2x dx. I always like to pause at this point, clean up all my minus signs, move numbers out in front. So I would write this as negative 1/2 e to the negative 2x. Minus a minus would make that plus 1/2 the integral of e to the negative 2x dx. And this time around, I would not write all of this back out again. We just did it. If this were me on a test, I'd be like, yep, that again. We're doing that again. So I'd have negative 1/2 x e to the negative 2x plus 1/2 of negative 1/2 e to the negative 2x plus a constant. And I think there's just one more question on here, right? Which is finding an area. We haven't found an area in a while. Feels like we haven't found areas for weeks. Oh wait, I guess we've kind of been doing it with probability, but you know what I mean. We haven't really found areas between functions for a couple weeks. So this last problem, we're being asked to find the area, find the area between y equals x and y equals x squared. And it says we can graph it if we want, but we don't have to. I always like to graph things, but I know some of the rest of you don't. So if I were to do this without a graph, I definitely need to figure out where these things intersect. So I would move everything to one side, factor out that x, and see that they intersect at 0 and 1. So I know my integral is going from 0 to 1. The only thing we have to figure out is who's on the top and who's on the bottom so that we get our subtraction right. So if I pick, there's a request to slide that up. Hopefully I slid it up enough. So if I pick a number between 0 and 1, I just need to know who is bigger. So fractions or decimals? Fractions, that's my choice too. So if x is equal to 1/2, then x squared would be 1/2 times 1/2 or 1/4. X wins. So I know that I should be integrating x minus x squared. If we graphed it, we would also know that. So if I do this, my integral of x is going to be 1/2 x squared. My integral of x squared is 1/3 x cubed. I'm going from 0 to 1, which means I am looking at 1/2 minus 1/3, which I think is 1/6. And I'm out of time. So for Friday, is it helpful if I make up more practice problems? Cool, so I'll make up more practice problems. I'll post them to Canvas probably tomorrow. And then we can go over practice problems on Friday or whatever else y'all want to do. So if you want to revisit any of the homework assignments or midterm problems or something, we can do that also. I hope all of your studying is going well. Not a problem at all. Have a lovely afternoon, everybody.